Elements are like people. Some of them just don't do anything at all. They don't react to whatever the situation is. That's this group here. Some of them are very generous and they like to give. They like to give an electron. They like to give 2 electrons. Generous, nice elements. And there's those who will take them readily, particularly these last few groups here. They'll accept those electrons with pleasure. Some people like to share. This group particularly likes to share, and that's sweet. But then there's those quirky personalities, those ones that are unpredictable. Fortunately, they tend to be generous. They're always giving a little bit. But how much they give depends on the situation. And that's these blue elements here, and to a lesser extent some of these and some of these. These are the polyvalent, or as I'll say this year, multivalent ions. We already mentioned the ones that don't become charged, the noble gases. We'll think about those that can form more than one charge and ask ourselves why. And we'll think about how we name them. This is Screencast 7.6. Okay, multivalent ions. It's primarily the D block right here. They form a +2, a +1, sometimes even a +6 charge, depending on the situation. To a lesser extent, it involves some of these green ones here and these black ones here. So, why are they multivalent? Well, let's take a look at titanium, which is somewhere in here. Is that it? Tantalum, titanium. There it is, titanium. It's 1s2, 2s2, etc. But if you look at this closely, you'll notice that it's got 2 electrons in its 4th shell. So you'd think 2 valence electrons. Yeah, it's going to lose those 2 to get a noble gas configuration. But it's missing 8 of the electrons in its 3rd shell. What's up with that, right? It has an unfilled inner shell. To cut to the chase, when that's the case, the charges are somewhat unpredictable. Interestingly, these 4 here, aluminum, zinc, silver, and cadmium, have, to my knowledge, never been observed to be multivalent. They're always the charges that are shown there. But except for those exceptions, these ones are multivalent. They have close energy levels. Between the 3D must be really close to the 4s, and therefore they have unfilled inner shells and possible charges are numerous. How do you name them? Well, you just see what the thing formed. Say it formed at +4. You write 4, so nobody's in any doubt. This is chemists doing the right thing. Examples. Titanium 4 chloride. Note that they use Roman numerals for some weird reason. This would be TiCl4, tickle 4. So that's because we know that the titanium is +4. It wanted to lose 4 electrons. Didn't obtain a noble gas, but it seemed to make it stable. TiCl2, I bet you could guess the name of that. Titanium 2 with Roman numerals, chloride. Iron 2 cyanide. Let's go ahead and write that out. Well, it's iron with a +2. Each cyanide is -1, so I need 2 of those. Use parentheses to show that there's not 2 carbons, not 2 nitrogens, but 2 cyanides, right, that are bonded together. This is Screencast 7.6.